So before I get started, I need to make a disclaimer here that even though I work for Airbnb, this is just my opinion. These are my views. These are not the views of my employer. All right. I suspect, given the crowd here, most people recognize this person. If you don't, that's Leslie Lamport, Turing Award-winning computer scientist. You've most likely heard of him either because of TLA+, which was mentioned a few times, which he developed, or because of the Paxos distributed consensus algorithm if you're in distributed systems, or LaTeX if you've done pretty mathematics, or I think Phil C's concurrent garbage collection is based on work by Dijkstra and Lamport. So very famous guy. But what I want to talk about today with him is this talk he gave back in 2003 in, I don't know how to pronounce that, Kiel, Germany, at Christian Albrechts University. And in this talk, it was called The Future of Computing, Logic or Biology. And he basically saw a path forward for how we think about software systems, right? And so one path, which is called logic, is really mathematics. I'm going to use logic and mathematics interchangeably. And so he says one way you can think about systems is you can think about them mathematically, describe them mathematically. So for example, here's a way to describe a simple system mathematically. Imagine like a one-dimensional string that's like fixed at two locations, right? -2, x equals -2, x equals 2. You start out by sort of stretching it out into some shape. Here I just picked hyperbolic cosine, right? So it's stretched out like that initially. That's how it starts. And then there's some mathematical description of how the state of that string will change over time, right? This is the one-dimensional wave equation. And if you have this mathematical description of your system, then you can reason about how that system is going to change over time. And I think it's no coincidence that if you look at the structure of a TLA+ specification, or that was the specification language that Lamport built, it looks kind of similar to the way you would describe a system with differential equations, right? You specify your initial conditions. Conventionally, you call that init. It's a predicate that says what are the allowed values of your state variables at the beginning. And then you specify another predicate, which is called an action in TLA+, which tells you how the system's state variables evolve over time, right? And that's how you describe systems in TLA+. All right. The other approach to think about systems is the biological approach, to think about systems the way we think about biological systems, which are extraordinarily complex systems which we humans really are not capable of understanding, right? And so we can understand aspects of biological systems. And here I have a picture of, this is a picture, well, really a drawing of the cellular structure of cork that Robert Hooke did way back in the 1600s. Right? So this gives us some aspect of a biological system, but really this is nothing close to the mathematical description of a system. And so here's what Lamport said during this talk. He said, when people who can't think logically design large systems, those systems become incomprehensible, and we start thinking of them as biological systems. And since biological systems are too complex to understand, it seems perfectly natural that computer programs should be too complex to understand. We should not accept this. This means all of us, computer professionals as well as those of us who just use computers. If we don't, then the future of computing will belong to biology, not logic. We will continue having to use computer programs that we don't understand and trying to coax them to do what we want. Instead of a sensible world of computing, we will live in a world of homeopathy and faith healing. It's pretty harsh. Unfortunately for Leslie Lamport, I would say that the path we took is the biological path. I think his fears have come to pass, and this is the way we deal with software today. Right? So I'm an SRE. Anyone else an SRE in the room? Oh, yeah, we have a few. Cool. Excellent. And one of the things I do is incident response, right? So I'm on the primary on-call rotation. When there's a high-severity incident, I get called in to help deal with that. And that means I spend a lot of time looking at software that breaks. And also, I'm really into that, as Isaac was alluding to. So like in my spare time, I also spend time looking at how software breaks. So I spend a lot of time thinking about this. But really, it's not software that breaks, right? Like if you think of software like a computer program, like source code, it doesn't do anything. It's an inert artifact, right? It's only like when it's running inside of a, on hardware in a system. And that's sort of the things that are break, right? Like a printout doesn't break, but it's only the system that's executing that breaks. So it's really systems that I care about. And in particular, the kinds of systems that we build today, these are complex adaptive systems. And I want you to think of them that way, because that's what biological systems are. And because of that, because the systems that we build are complex adaptive systems, they actually fail in ways that are similar to how biological systems fail. So it's not just like we get homeopathy and faith healing from biology. I think biologists would be a little insulted by that framing of it. But there are other ways we understand biology, and we can get insights from that world. So for example, your heart. So this is sort of mixing math and biology here. This is the Frank-Starling law, or Frank-Starling curve, and it describes a relationship between the volume of blood in your artery, your ventricles in your heart, right? When your heart relaxes, when it goes into what's called diastole, it relaxes and then blood flows into the ventricles, and that's the ventricular preload on the x-axis. And then based on the volume of that blood, when your heart pumps, the volume of blood that gets pumped out is proportional to that. That's the stroke volume, right? So if your heart wants to do more work, then it will put more blood into those ventricles. And it's there's a linear relationship up until a certain point, right? And then after a certain point, even if more blood is flowing into the ventricles in diastole, you're not getting more work out of your heart, right? Your heart reaches some limit, and then it can't do work anymore. And so, like our heart, everything we deal with, all the systems we work with, they have a limit. And when you hit that limit in your system, very bad things can happen sometimes. And the term I'm going to use for that, for when systems get to their limit, and bad things potentially happen, the word I'm going to use is saturation throughout the course of this talk. And the reason I use the term saturation, some people do use it in our industry. You will see it sometimes in incident write-ups. You will see it if you follow Brendan Gregg, who's a performance engineer. He will talk about diagnosing saturation in terms of performance issues. But the reason I'm using it here is because, I'm a fan of this research field called resilience engineering. It's a subfield of safety science, and they try to understand across a wide variety of fields, like aviation and space flight, nuclear power, all sorts of transportation, all of the safety world. How do systems sort of become resilient and maintain that resilience? And they take a lot of inspiration from biological systems, which are resilient, right? You as an organism are a pretty resilient thing. You can deal with a lot and still keep going. And I'm in particular a fan of David Wood's, and I'm going to talk a lot about sort of the models that he proposes. And one of the things that he talks about a lot in his work is the idea of saturation, and that resilience requires managing the risk of saturation, because saturation is the kind of thing that takes complex adaptive systems out. Okay, so here's a dot, and I want you to think of this dot as your system. Now, by system, actually, I don't even mean just the software and the hardware, but I mean the entire socio-technical system. And by socio-technical, I mean not just the software and hardware, but I mean the people that are involved in writing the software and validating it and deploying it and operating it, as well as all the tools that they have to use to do their work, right? So all the deployment tools and test tools and IDs and agents these days, right? Those are all part of the socio-technical system. Now, so imagine your system, which is this dot, is a point in some sort of higher dimensional space, okay? And then there's this envelope around it. It's enclosed inside of a region. And Woods calls this region the competence envelope, right? And as long as your system stays within its competence envelope, then things are great. Your system's healthy, your users are happy, everything is good. Now, the problem is that there are stressors that your system is going to experience that are going to move it around inside of that envelope. So for example, let's say there's a spike in traffic that you get, or maybe there's a transient network problem, right? So there is a spike in traffic, but you're provisioned to handle it, so you're good. Maybe you have a transient networking issue, but you've got retries, so you're good. Maybe someone introduces a bug, but you actually catch it because you have a tool like antithesis, or maybe you catch it in staging, or you roll back quickly. You've got or canaries or something. All that stuff is great. You're within your competence envelope. You can deal with those things. The problems happen when your system moves so far away that it goes outside its competence envelope. And in Woods' framing, that's what saturation is. When a system is pushed outside of its competence envelope to the boundary of what it can handle, right? So this is sort of a very abstract way of thinking about systems. It sort of applies across all different domains. But let's get a little more concrete about what saturates in our world, and specifically in the world of software, rather than in heartbeats. So software is sort of this ethereal thing, right? It's mind stuff we talk about, but ultimately it's got to run on some kind of physical hardware, right? I used to have this sticker on my laptop, right? Like the cloud abstracts away a lot of compute stuff for us, but like somewhere, probably in Northern Virginia, there is a data center where that software is running. And so one thing that can saturate, one physical thing, is CPU. And now, we live in a multi-core world, so we get multiple cores in our chips. But if you want to run more tasks than you have cores, well, some of those are going to be stuck waiting in a runnable state until they get a chance to execute, right? And so when that happens, we say the CPU saturates, right? And you're stuck waiting for your task to be able to run. And we saw, I think in one of the lightning talks yesterday, someone from Jane Street was talking about how they made a performance change, and that ended up leading to CPU saturation. They had 100% CPU. And that sucks, right? Having to wait, and you'll get timeouts, and your users will not be happy. Since this is kind of a PL-heavy audience, I think what's most directly on folks' minds is memory. We just had a whole talk about memory safety. I'm more concerned in the reliability space about running out of memory. Right, and Richard Hips was talking the other day about how malloc always succeeds in Linux. It will always give you back virtual memory, and it was hard for him to do testing to get malloc to fail because of that. So he was concerned there. My concern is not there with the malloc always succeeding. My concern is that the services that I care about run out of memory, and then the dreaded killer comes in, and the kernel will randomly terminate one of the processes, probably the one that took up all the memory. And so we have metrics around this because this is not uncommon that we will run out of memory. Garbage collection is kind of an interesting thing. So if you use a stop the world garbage collector, like G1GC, which is the default in Java until pretty recently, what happens is that garbage collection has this interesting property that it changes memory saturation to CPU saturation. So as your process goes under memory pressure, right, what can happen is you have these stop the world phases where all the application threads get blocked, waiting for the GC threads to process through the phase so that it can free up memory so that it can keep going, right? And so you end up with CPU saturation again. There's still disks, right, are still around, even SSDs. They're cheap, you get a lot of storage these days, but they're finite, and you still see problems with people, running out of disk space. I've seen it. One of my favorite examples here is when there was a service that started throwing errors. The errors were actually harmless, didn't affect the customers at all, but the errors were logging full Java stack traces, and it generated so much logs that the logs filled up the device, and that ended up causing a problem for the system. Has anyone ever seen this error, but actually they had plenty of space left on the device? Yeah. This was very confusing to me the first time I saw this. So you can get this error even though you have plenty of storage. And the reason is that there's another limit in file systems, at least on Linux, at least the ext file system, and that's the number of inodes. There's an inode data structure for each file you create, and there's a fixed number based on when you create that file system. And if you use up all those inodes, if you create many, many, many small files, you can very confusingly get that error message. And that is a fun lesson to learn. Here, I'm actually going to just grab water for a second. Glad I have this. All right. So the one last physical resource I'll talk about, this is a terrible drawing, but I tried, in Excalibur of a network card, is network bandwidth, right? That's another physical resource you have, and it's not as common, but you can saturate that, right? And once you run out of once you use up all the bandwidth, either on your network interface card itself or in the network links between, then you just can't push any more data through at that rate. So those are the physical limits, but we also have a ton of virtual limits that we face, and the virtual limits are there for a good reason. They're there because they basically act as fail-safes, right? In the same way that you have a circuit breaker that will stop the current from flowing in your house well below what the wire can handle, is because if you didn't have that circuit breaker here, you could have a fire, right? Like you could, if there's too much current flows, your house could burn down. So we deliberately engineer systems to fail earlier where the consequence is lower than if we let it go all the way to the physical limit, right? Which on the one hand is comforting, but on the other hand, if you're a victim of hitting a virtual limit, that's maybe not so comforting. So you will see various places where we use pooled resources. Part of that is for performance, because to acquire a new resource, like spin up a new thread, say, or a new connection to a database, takes some time, and it's nice to be able to have sort of a cache of them. But also, once that pool runs out, if you need another thread to run a task, or if you need another database connection to make a call to the database, you're out of luck. You're stuck waiting for the resource to be returned to the pool. Bounded queues. We can make queues that are unbounded. It's probably even easier, but you really want to make your queues bounded as much as you can for the reason where you want to fail safe, right? But if you have a bounded queue and that queue is full and you try to enqueue something to it, you're either going to be blocked waiting for someone to pull something off that queue, or you're going to get an error back, depending on how that queue is implemented. And these things are all over the place, right, in distributed systems. There are queues in places you probably didn't even know existed. Just sort of a random example, if you wanted to know the size of the queue for the incoming TCP connections on your Linux machine, you can use syscontrol. On this one, happened to have 4,096. And then there are some limits that are not within your system itself, but are part of another system that you depend on, right? So you're calling into something else, and there's a limit there, and that limit is going to impact you. And the primary example, at least that I can think of, are rate limits, right? Anyone ever get a 429 error back? Yeah, you have saturated that sort of connection, the amount of requests that you have. You don't know if you've hit some physical limit, but your service provider has said, hey, I'm not going to take any more requests from you, you're hitting me too hard, right? And I've seen many incidents that involve 429s. So let's look at some real incidents that have happened and people have written about publicly. Right. The first one happened a few months ago. This happened to Blue Sky. And the thing they ran out of, what saturated, was ephemeral ports. Right? And I thought this was really interesting. So if you look at the error message on the bottom, right, bind address already in use. Now, if I see that, my initial assumption is, hey, I tried to listen on a port, like port 443 or something, and something else was already listening on that port, right? And so that's why I'm not able to bind to it. But that's not what happened here. It's not the server-side port. So in TCP, when you make a TCP connection from the client to the server, the client also needs a port. And so what happens typically is that the operating system will just randomly assign you an ephemeral port, right? So if you specify port 0, like at the bottom from the client, which is 127.32.0.1, it will pick a port for you. But those ports are a finite resource. And in this case, because it's sort of funny, it's not like there was a lot of traffic, but the payload size and the individual requests were very, very large, 15 to 20,000 URLs. And that ended up spawning like a ton of Go routines, and they saturated the connection. And the real irony here is that that connection is to localhost, right? That connection is to a process that's running on the same machine as Memcache. And so there's a lot of great detail. I recommend going reading Jim Calabro's write-up, and it's really nice. I really appreciate when a company like publicly talks about the details of their incident. There's another one that happened to Slack a few years ago. This one was written by Lorin, who's no longer at Slack, but she did their best incident write-ups. And this was kind of a complex one that involved a lot of saturation. I'll see if I can explain this here. So this happened to Slack, like I think on a Monday after a holiday, right? And so there was a large volume of traffic that went in through their web tier, hit their transit gateway, and their transit gateway saturated, right? And so it started to get overloaded. And then that meant that the calls from the web tier to the transit gateway, those threads got blocked waiting because the transit gateway got slow. And the web tier auto-scaled on CPU utilization. And now when threads block, they are not using CPU. And so the web tier actually started to downscale because of that. Now, actually, they also have another rule where they scale up quickly if there are too many threads, right? So they designed for that, right? So what happened was there were too many active threads, and so they quickly scaled up the web tier auto-scaling group. The problem was that quick scale-up overloaded their provisioning service. So there is a service that provisions new instances as they come up inside the auto-scaling group. And that thing hit too many open files. And it also hit some AWS quota, right? And so it could not provision the new ones that came up. So new ones that came up couldn't take traffic. And then they actually hit the limits of that web tier ASG. That ASG hit its, it's configured to a max size. And so there was like 4 different kinds of saturation all going on at the same time in this incident. And once again, I recommend reading the write-up. It's really a lot of great detail on what happened there. The last one I want to talk about happened also fairly recently in San Francisco, which I thought was a really interesting failure mode. So back in December, there's this big power failure in San Francisco. If you have been to San Francisco recently, you will see there are Waymos all over the place now. It is sort of Waymo Central. And so when there was this power failure, the traffic lights went out, right? Now, when traffic lights go out, we treat them like 4-way stops, and Waymos treat them like 4-way stops. But in some circumstances, Waymo will also do what they call a confirmation check when this happens. They don't explain what that is. My assumption is that they are calling home when there's a human teleoperator checking to see is this actually safe, but I don't know for sure. But all I know is that they do confirmation checks in some cases when a Waymo hits an intersection where the lights are out, right? And they got overwhelmed by those. So there was this huge backlog of confirmation checks they couldn't get through because there are all these lights that were out in San Francisco that affected all these Waymos. And so all these Waymos were just stopped at these intersections during this time, right? And the funny thing is, of course, they had put that in for safety reasons, right? And what happened was it caused an issue. And they wrote a blog post about it as well. This is all coming from the Waymo's official blog. All right, so those are some different kinds of saturation. Now I want to talk about the different ways that systems can saturate. So the way we generally think about systems saturating is there's some sort of increase in load on the system, right? That's the most common one. Sometimes, often external traffic will do that. Sometimes it's what I would call bad external traffic. It's traffic we don't want. Usually that's bots in some way. Maybe it's scrapers. Maybe it's some automation that's gone crazy or just doesn't respect your site or whatever. But also sometimes there's external traffic that I would call good, that you're getting more users or more usage of your service. And so you sort of want that to happen, but you can't handle the load. And I thought this was interesting. This is 2 tweets, one from an Anthropic engineer and one from an OpenAI engineer, about 3 days apart, both of them talking about how they are faced with the risk of saturation, that they have to make changes internally because they are getting overwhelmed by the increase in load on their system because of how successful these companies are being. Now, if you have a sudden spike in load, we have like a cute name for that, right, in our industry. We call that a thundering herd, when all of a sudden you get a lot of traffic coming into you. We also, in a particular case, we have a term, retry storm. Anyone ever heard of that, retry storms? Yeah. So you can imagine a service starts to get overloaded and it starts returning errors because of that, and then all the clients retry, or There may be automated retries or sometimes manual. Have you ever, as a user, like, I can't hit this site, I'm going to keep trying over and over again? Yeah, you're a human retry storm, right? You are making it worse. And it's a very natural reaction. There's traffic amplification. I think some people call this fan out, right? Where there's not that much traffic going into a particular service. And I live in like microservice land, so you can imagine these as being two microservices in a larger microservice architecture. So some traffic is coming into service A, and service A, for whatever reason, makes many, many calls for each one to service B, and that overloads service B. So it seems like you're OK from the outside, but you're actually overloading one of your internal services. And then one of the most pernicious saturation failure modes is when you have a resource leak. So it could be a memory leak, or it could be a leak in any of your resource pools, like thread pools or connection pools or whatever. And I call this pernicious because as an SRE, our most effective heuristic at bringing the service system back to healthy is to ask, like, what changed when we started to see impact, right? And the problem with resource leaks is that the time of change is not close in time to the time of impact if it's a slow leak, right? And so nothing happened at the time of impact other than you actually reached saturation. You ran out of resources. But that doesn't tell you that the leak happened, 3 months ago. My favorite of this case is you will sometimes see companies where the services have resource leaks, but they deploy often enough that it masks that, and then they have a lock, like a deploy lock, for safety. And then what happens is that exposes those resource leaks you didn't even know were there. So that the leaks might have been there months or years before, but you don't see it until the circumstances change and expose them. Sometimes someone will implement something that is functionally correct, but eats up a lot more CPU or memory than you were expecting, and then that actually takes out your service. This was a fun one from Cloudflare back in 2019, where one of their WAF rules had a particularly expensive regex, which did a lot of backtracking, which led to CPU saturation, and I think they were like 503ing on all their sites, right? And they have a lot of good detail about that at theirs as well. So sometimes, companies often have some internal processes that are running in addition to like online traffic that's coming in, and those internal batch. Ideally, you have segregation between like your online and offline traffic, but there's usually some nexus points, and these internal batch jobs can knock you over, and you sort of see, well, why did that happen at some specific period of time, right? And because some new batch job started. I've seen cases where someone does some sort of ad hoc query to a database, and that right, that happens to take out the system because it's so expensive. You didn't realize it was going to happen. I saw someone do this once and it just happened to be it wasn't the specific query itself, but they were using some like GUI application that they were connecting to a Cassandra database, and it did some really expensive query, and it took the whole thing out. And sometimes it's just plain misconfiguration, right? Sometimes your limits are just set too low. And that's fine for nominal, but when you hit peak, you don't realize until then that you set your rate limits too low, or whatever other limit you have. So my claim here is that you can't actually avoid saturation. Like, you are eventually I will predict that eventually, within this year, I would say, you're going to have an incident that involves saturation in some way. And the reason I am so confident in saying that, not just because I've seen many of these, is one, just because of the fundamental nature of reality, right? So we have a finite amount of resources available to us, right? Which means you never are going to have like infinite headroom. But more importantly, and something that's actually come up several times, I think, in this conference, is that we all face production pressure, right? We all face pressure from the business to deliver what is perceived as value to the business, even if we are concerned that there are other things that we should worry about in terms of quality, or we want to spend more time daydreaming, as Marianne mentioned, right? Like, production pressure takes away that time, the thinking time. And like, we can try to push back on it, but this is inevitable. You are always going to face this. You are never, if you ask an engineer in any field, if you had much more time, could you do a much better job? They would all say yes. Like, we all face this, and there's no way around it. And so we have to just sort of navigate it as best we can. Finally, there are some limits out there that you just don't even know about until you actually run into them. So I made sort of this, I like to make sort of jokey, like, suggested interview questions. And I made this one a few years ago. And I thought it'd be a fun question to ask SREs, like, tell me about a time when you learned about a limit only when your system hit it, right? And the reason I think this is a good question is because then I think you would get a good story out of them. I don't know if I would be able to assess how good they are as SREs, but I'm just looking for good stories. And I got a lot of responses on Twitter at the time, and I actually started a, so I actually started a page on GitHub called Awesome Limits, where I started collecting these, because people kept telling me about different limits they had. Unfortunately, because of like the Twitter exodus, this is sort of link rotted, so the original sources are not always around. But the point I'm trying to make here is that you're never going to be able to fully design your way out of this problem, right? It is always going to be a risk that you face. So going back to the model that Woods had about the confidence envelope, is that you can improve your designs and increase your envelope size, right? Every time after an incident when we say this is never going to happen again, we're going to design our system so that we can handle that particular failure mode, you're expanding your confidence envelope to deal with more types of problems, and that's good, but you can never expand it infinitely, right? There's always some limit to your system. And that's why people like me have to carry pagers, right? I mean, this is the reality. I mean, I would love it if AI took my job. I'm like, take my job, please. I don't want to be on call and get paged at 2 in the morning. But I just don't think it's going to happen. Because I think that for the foreseeable future, humans are going to have to intervene, right? Because like, there are things the systems can handle by themselves and auto-recover, and they do that. But there are many cases where they don't. And for that, you've got to bring in the people to help recover from the saturation. And when that happens, right, when your system is in saturation, you're having an incident, you're throwing 503s or you're just hanging or whatever, something about your system has to change, right? Like when an incident happens, when it gets mitigated, somebody did something almost all the time, right? Unless it's self-resolved. Sometimes it fixes itself and no one knows why. Those are scary cases. But in the majority of cases, someone does something to bring the system back to healthy, right? And so that's some change that the system is actually imposing on itself. And that's what the resilience engineering folks mean by resilience. It's the ability of a system to change itself when it runs into a problem, when it hits a situation that it wasn't designed to handle. Right? So once again, going back to the model, so once you hit saturation, what resilience is the ability to extend the confidence envelope, to make a change to your system so that now your system is back within that confidence envelope again and is healthy. And this is why, going back to David Woods and his paper, he uses the term graceful extensibility to describe resilience. Because resilience is kind of an overloaded term. People use it to mean different things. He means it he uses it to mean, did someone get paged? Is it incident IO? He uses it to mean the ability of a system to extend its confidence envelope when it hits the boundary. That's what graceful extensibility is to him, and that's what resilience is to him. Right? So to be resilient, we need to be able to adapt to cases that we didn't think of in advance, right? Because if we thought of in advance, we would have designed them out, and we would be able to automatically handle them. So we need to be able to handle situations that we did not think to design for. Right? And the expression I love the most about this is like, to be resilient, we need to prepare to be surprised. Right? That's the name of the game. I did not realize how dry my mouth was going to get here. Okay, so how do you do that, right? And so we don't know exactly what we're going to need to do during an incident, but we know we're going to need to do something. Right? And so what you want is optionality. And right, the more knobs you have available to you during an incident, the better positioned you are to be able to deal with it. Like you don't want to have to build new tools on the fly. Like I would say the two worst times to write code are A, during an interview, and B, during an incident. And these are both sort of like high consequence, time pressure environments where, like, if you do nothing, it's terrible, but if you do the wrong thing, it's also terrible, and all eyes are on you, right? And so, like, this is not the time. Sometimes you have to write code. I've done it, but, like, you want to avoid it if you can, which means the more options you have at your fingertips when it happens, the better. Right, so you want to be able to have a lot of stuff. This is probably like, you know, motherhood and apple pie stuff. Everyone probably has this stuff. But you need to have like break glass so you can do like quick changes to production that you would not normally do. You don't want to have to wait for a lot of validation stuff to push stuff through. You want to be able to know how to do things like, okay, I need to cycle all my pods, right? That's like basically restart all of my containers in a particular service quickly. Or I need to be able to quickly scale up a service, right? Often, like, you know, the auto scaling has hit the limit or whatever. We need quick scale up, get more resources, get out of saturation quickly. You need to be able to, ideally, you know, do a quick rollback. Sometimes you can't do that. To be able to do a quick roll fix forward, right? And if you have a process that's designed to prevent bugs and there's lots of like gates you have to get through to get it out to production, that's going to suck during an incident unless you have a mechanism to be able to do that quickly. Which means you have to have thought in advance, how am I going to be able to quickly roll things out? Because now you're balancing two different risks. Dynamic configuration is great, right? So feature flags are an example of this, right? So ideally, you know, if you're hitting some kind of virtual limit, if you can dynamically set that limit rather than having to like go and edit a config file and push it and all that, you're going to be able to respond much quicker. So the more like feature flaggy dynamic config knobs you have, the more things you can actually do. A particular example is a lot of systems are rule-based systems, right? So for example, rules that block certain kinds of traffic is one, and so you want to be able to quickly say like add a rule to block certain kind of traffic, or maybe one of your rules is misbehaving and you want to be able to quickly remove that rule, right? Or you want to be able to block a certain query to a database. You don't know where that query is coming from. So the ability to add and remove blocking rules quickly is really useful during an incident. But all these knobs, they're only useful if you know that they're there and you know how to use them. Because if not, then they're not going to do you any good. And so it doesn't just take the knobs, it takes operational expertise. You need people who know what they are doing during the incident to be resilient. And operational expertise means that you need people in your organization that know the system, right? And in particular, the challenge there is that you can't hire for that, right? You can hire people who have general experience in the industry, you know, and they say, oh yeah, you know, I've worked with these databases before, or I've worked with JVM apps, or, you know, I know this, you know, there's a CDN here, and there's an edge service, and there's an API, yeah. But you don't know the details of the particular weirdnesses of the internal thing that you're dealing with, right? So you can hire for sort of potential for this, but you really have to grow this expertise inside of your company. There's no other way to get it on your particular system. And so there's two ways, I'll talk about two, the two ways that I know of to get better at this, to improve operational expertise. One of them is just to respond to incidents, right? The way you get better at dealing with incidents is dealing with incidents. And I actually think that if you have not had any incidents for a long time, that is a risk, because you are losing those muscles that you need to be able to respond. And so that's actually dangerous. So there's an optimal number of incidents, and it's not zero. And so this is experiential learning, right? This is the learning we get by doing, and there's really no other way to get it besides that. But then there's another way to learn, and that's to learn from the experience of other people at the company who are responding to incidents, in particular the ones who are really good. And I bet everyone at this company, everyone at this conference, I bet who works at a company that has, like, you know, has to deal with incidents, knows who the people are who are really good, who tend to jump in and, like, you're like, oh my gosh, thank goodness this person is here. And so learning through people like that is called vicarious learning, right? You're learning from the experience of others. And so in my view, I'm very opinionated about post-incident stuff. And to me, a good post-incident process, and by that I mean what they call post-mortem, like the incident write-up and the incident review meeting, like those are good if, as a result, people are getting better at operations, right? If they are actually improving operational expertise. But to do that, these artifacts, right, the write-ups and the review meetings, they have to discuss how people dealt with the incident, right? Like, you need to see those people's experiences. Where were they looking? What signals were they seeing? What did they, remembered? What dashboards did they look at? How did they know to do X, right? Even like what red herrings they went after, right? Like that's going to happen, right? This is we're getting ambiguous signals during incidents. Like, AIs can't one-shot them because humans can't one-shot them. And so there's a process by which we figure out what the heck is going on, and you want to get that information about how the people dealt with the incident, not just like what broke and how we're going to make sure it never happens again. So I'm at the end here. So to conclude my talk, my like pitch here is don't just focus on the design aspect, on expanding the competence envelope. Like, that's a good thing. After every incident, you want to expand it to the new failure mode you didn't realize you had. You want to be able to do that. But you also want to improve in your organization the ability to extend that confidence envelope when you hit that saturation point. When you're in the incident, how do you get better at changing your system to recover from it? And so, we have finite resources. You only have so many engineering cycles. So my pitch is that you really want to allocate effort to both cases, right? And David Woods would call this net adaptive value, where you're balancing increasing your competence envelope, improving your design, with improving your ability to improvise. Like, Hillel improvised yesterday when his laptop went down and he had to use a different laptop, right? He had to improvise a solution. When your design exceeds its limits, the system exceeds its design limits, which it is guaranteed to do. That's it. Thank you.
So there have been some times when I've been able to resolve an incident by logging into a production database and doing something. And it has been very nice when it's like, oh, good, now it's solved. But it's also like, I could light everything on fire by being logged into that production database. And so and there have also been times when I've known that if I could have just logged into that database, I could have fixed it. Or if I could have just like accessed the server to make this deploy manually, like we would have been done. But instead I'm waiting on this dumb CI pipeline that's taking an hour or something. And then everything's on fire and there's nothing I can do. So like, how do you balance giving people ability to do ad hoc stuff while not letting the junior developer drop the database or something, yeah.
Yeah, so I think the way you do it is you make it straightforward to break glass, but like someone has to be able to approve it. So like at Airbnb, the way we do that is you can request an emergency permission, and someone from my team can approve it. And we will if it's for an incident, right? So if we see, and you have to say which incident it's for, right? And so there's a quick process by which you can like request an emergency permission, and there's a process for approval, but there's another human check so that if someone's like is doing something irresponsible, then we'll catch that and say, no, we're not going to give you that permission. You don't need that here. But there are people who are like, no, we don't want anyone to ever be able to access the database directly, right? And I've seen cases where people like try to work around that during an incident because they really need to do it. And so I am of the opinion that you always want to be able to have that break glass option available to you to be able to hit that database directly. I mean, but usually you can reach out to someone on the database team to, I've seen where you have to relay it to someone else. It's annoying, and that increases the risk. But like everything is again, like you're always trading off risks, right? There's no like more risk, less risk, right? Like it doesn't work that way. And like the slower you make things, like the more checks and gates you add during regular processes, like the harder a time you're going to have during an incident. That's going to slow you down. And so you need a way to make dangerous changes, because not making the change is even more dangerous, right? Like that's sort of what it is, right? In the case where not making the change is more dangerous than making the change, you need a way to be able to make the change. But you've got to get buy-in from your company that it's worth to do that. Right.
Hi, so like yourself, I'm both a fan of formal modeling and also a fan of David Wood's school of resilience engineering and so on, right? And so I wonder if you could clarify the point about how there is this idea of our systems being logical versus biological, because it seems like you went to a lot of the, like, let's just embrace that they're biological and, deal well with that. And I guess I was wondering if there was also a point of, like, could we be making choices that at least put it in the direction of acting logically. I wonder if you could square that circle if you had a thought there.
Yeah, so I mean, I think the logic biology dichotomy of Lamport's is like ultimately not correct. You know what I mean? Like, I mean, I think he's correct that our systems are now too complex for humans to understand. But I think there's definitely a place for like logic and hey, I'm a formal methods fan, and formal methods for design, because like in the design, like you cannot, I don't think we'll ever be able to design the entire system formally, but we can design parts of it formally, right? And the way that I think about both of them is that like, I have a bunch of tools in my toolbox, and all those tools help me think about things, right? And I'm thinking about like designing a new distributed system. The formal model is useful for that. It's useful to help me think about the system in ways I wouldn't have otherwise. It forces me to think about like many different aspects, right? Similarly, like the resilience stuff is a model, and it forces me to think about like how do we prepare for incidents in the future when things are going to break. With the design, I want my designs to be better, right? I want to expand that competence envelope, right? Like I want my designs to get better, but I recognize that they're never going to be perfect, right? But we should always strive to be better, right? That's why we're all here, right? Like we want like. I don't want to be a fatalist and say like this is as good as it gets, and like I want us to get better, but I also just want us to be realistic about what we're up against.
Thank you for the talk. Brilliant stuff. We know postmortems are a great learning experience when used right. What are your thoughts on premortems?
So I need to ask you what you mean by premortems. I can tell you what I understand by premortems. So for me, so I'm a fan of, oh my gosh, there's this idea of premortems. Gary Klein, I don't know if you know Gary Klein. But anyways, Gary Klein has written about premortems. And a premortem, he talks about that in terms of a project, not necessarily in terms of a system. But I like his premortem model a lot. And he's like, you're at the beginning of a project. You sit down with everyone, and you say, OK, imagine it's a year from now. The project has failed completely. It's been a total disaster, right? You're looking at crystal ball. I want you to tell me why it failed, right? So you go around the room and you have people write that down and talk about them. So not like what could go wrong. No, imagine that it failed. It went wrong, and capture that. And so I love those. But that's a project-oriented premortem. So that's what I think of in premortem. I don't know if you have something.
Yeah, so at work we do a lot of tabletop exercises and stuff like that to simulate certain simulations. And what we do, not necessarily hands on keyboard, but just hand waving over different things. It's okay sometimes, and other times it feels like a giant waste of time. And I was kind of curious what your thoughts were. Where's the highest value typically when you do these things?
For tabletop exercises?
Yeah.
Yeah, so I find them very useful, but I find it's the hardest part of tabletops is getting people to run them, right? Like it's a lot of effort. And I will tell you, there was a guy. So I'm a big believer in that sort of simulation-y stuff, and tabletops. I've done them. I always get nervous when I'm in the hot seat in a tabletop exercise. There's even a company, Uptime Labs, which now does like Slack-based tabletops. Right? They're an incident simulator, and I think they're pretty cool. So I'm a believer in tabletops, but I've seen them fail in the past because like it's so much work to come up with new ones and to run them that like nobody wants to do it. And so if you can find someone who's willing, or your team is willing to create a culture where that happens, that's fantastic. Every team I've been on has started it, done it for a little bit, and then stopped. And so I have not seen a way to keep it going. Yeah. Yeah. I wish that like there was a way to reduce the effort to run it, because it's an expensive thing to do.
Marty, one more quick question. Okay. Yeah, thank you for the talk. So quick question about after incident handling. Is there a process by which you determine that the system needs to be modified so that another incident like that doesn't happen again? Or I guess what I'm trying to ask is there a process that you guys go through to determine whether or not you actually need to make a change to the system, or you chalk it up to, it just kind of happened?
No, I mean, there's typically a post-incident process where people define corrective action. For any like high severity incident, there's always like corrective actions defined. So we have a regular process around that, right? So there's like a write-up gets written, there's a review meeting, you review the action items and things like that. I think that like my general complaint about that is that all the oxygen, I feel like we spend too much time early focused on that. Like I want to understand the problem a little more. There's usually, in the places I've worked, it's not like, oh, people are just like, yeah, it happens. No, like they're like, no, we need to do X, Y, Z, W for this specific failure mode to not happen again. And that might even make things worse later on. I enjoy tracking like, hey, this incident happened because, well, not because of, but like a contributor was a corrective action from a previous one. So I am personally worried about like overdoing corrective actions to do something and not spending enough time understanding like how the incident happened and how people responded. But depending on your context, I can imagine people being in places where there's not enough attention paid to the corrective actions.
Okay, thank you.
All right.